Start your call.
Hi everyone, welcome to this week's ASAP seminar. I'm very happy to host today's talk. We are thrilled to have Jianyu Zhang, a fellow year PhD student at NYU, advised by Neil Bolton and Yan Lequan, and soon to be research scientist at Meta Field. Jane will be talking about AI for the open world, the learning principles, a very timely topic, especially as we push towards general purpose models that can handle tasks beyond narrow benchmarks. In particular, he'll share insights behind the memory mosaic architecture and discuss the principles that might guide learning in open-ended settings, such as rich features, disaggregated representations, and inference time learning. Please join me in welcoming Jianyu. I'll hand it over to you.
Thank you. Thank you, Songlin. I will start. Okay, so today I'm going to introduce this work called AI for the Open World, the learning principle. It comes from my PhD thesis that also included a lot of work with cooperation with many smart people. So let's briefly review what kinds of AI did we achieve. So we achieve AI for artificial environment like chess, Go, Atari game. We also have some AI for specific real-world tasks like handwriting or face recognition. I call it AI for the closed world because they are competent on specific tasks. That means a narrow range of tasks. Because of that, one can collect a lot of data because of the narrowness of the domain. One can also define a precise criteria of success. For example, the game score in many games, precision recall in many classification problems. And this criterion not only reveals whether a machine has achieved a goal or not, but also reveals how a machine falls short of the goal. That means human designers can fix the problem one after another until the machine is damn good enough for the task. At the end, instead of proving that our machine is intelligent, we often find satisfaction in proving that we are intelligent because we create all these kinds of criterion, all these kinds of shortcuts and engineering. That means the AI for the closed world rely on prior knowledge of human designers. People need to provide the task-specific prior knowledge for each task. Okay, this is clearly not what we want, at least not what we want for AI, right? So what do we need? I call it AI for the open world. That means AI should solve any task that a human could possibly undertook. With few examples, because we cannot wait too long for AI system to learn a new task, right? For example, in the self-driving, we want the AI to learn how to drive within, let's say, a few seconds or a few minutes. Otherwise, we die. Also, we do not want the AI system to heavily rely on prior knowledge of human designers, because we do not want to assign one human designer to one task. We have a lot of tasks, right? So in short, the AI for the open world require machine to learn a wide range of tasks, new tasks, quickly with few examples and less task-specific prior knowledge from human being. Then having this definition of AI for the open world, the question is that can we translate the success in closed world to open world? Like, let's say, can we extend from the narrow range of tasks to a wide range of tasks? Well, here is an idea. We can train on everything. We can train on all possible text from internet or image from internet. It's basically the mainstream belief of a foundation model. But there are two critical problems. One is that this approach is computationally infeasible. because combining two pieces of knowledge results in a new knowledge, leading to an exponentially large number of possible combinations. That means it is impossible to pre-compute all combinations, right? And the second issue is that this approach is practically implausible because the pieces of knowledge could change over time. The knowledge yesterday may not be the knowledge today and not tomorrow. So the answer is no, we cannot translate the success in a closed world to open world. We need some other learning principle to build AI for the open world. And this talk explores such learning principle and the corresponding techniques to help build AI for the open world. So to target on the 3 properties of AI for the open world, I introduced 3 principles. So the first one is rich feature, a richer set of features beyond the need of ID generalization. It helps to learn a broader range of tasks. And then it's disentangled representation. It reduces the number of required example on unseen tasks because different features are disentangled. We can select the feature based on what we need. To reduce the relying on prior knowledge from human designers, the third principle is inference time learning. It is a memory-based method at inference time, leveraging rich feature and disentangled representation from pre-training states. Okay, so let's jump into the first principle, rich feature. So by the way, I will briefly introduce the first one, rich feature, and focus more on the second one and third one because it contains the memory mosaic. I believe you guys are more interested in that part. Okay, so rich feature. The goal is to create a richer set of features beyond the need of ID generalization. We want to help the system to learn a broader range of unseen tasks. So I will briefly introduce the benefits of rich feature when handling unseen tasks. And then I want to discuss the question that can we construct a rich feature by simply scaling up ERM training, like big data, large model, things like the foundation model. At the end, I will introduce some approach to construct a rich feature. So let's start with some warm-up case. So there's one background that is in stochastic optimization in deep neural network. Actually, many regularization, including L2, early stop, they has a sparsity bias. Means when you add L2 regularization, you have sparse feature. Okay, from this theoretical work. Then I do a simple experiment. I pre-train the ResNet on CFAR 10, the first row. Then I linear prop the learned representation on CFAR 100. Well, as expected, L2 VGK, the second column, the first row, help ID performance on CFAR 10. There's nothing to surprise because that's what we know. But let's look at the second row. We can see that the L2 VGK actually hurt the OT performance from 49 to 29. That's a lot. Means from this tall example, we can see that rich feature help the learning of unseen tasks. One can compare the one with or without L2 VGK. Well, there are a lot of other examples in the paper, but I will only use this tall example. Let's go to the question that can we find the rich feature by scaling up ERM per training? To answer this question, I will compare 2 representations with the same number of parameters. One is I train a large model at a ResNet or Vision transformer with supervised or self-supervised object, this one. Then I take the penultimate layer as a representation. That means I remove the last linear classifier, okay? That's the first approach, the first representation. I also have the second representation that is I train multiple smaller models and the same data with only different random seed. That means I change the network initialization and example order in optimization, but with the same data, same hyperparameter, and same training process. Okay. Then I take the penultimate layer of representation and concatenate. Okay, the second one. So I have two representation. Now the question is, which representation is better for the learning of unseen tasks? For example, I can use a linear probing or fine tuning. Well, here is an example on supervised transport learning. I take a ResNet, pre-train on ImageNet on the left, and linear probe fine tuning on other tasks like let's say CFAR 10, CFAR 100, naturalist on the right. And the orange curve shows the performance of the first representation. The blue curve shows the performance of the second one. So we can see that for IID performance, actually the big model outperformed the concatenation of smaller model. So the x-axis is the number of parameter. Sorry, the y-axis is the performance. We can see that ResNet 50 with 4-time bandwidth already outperformed the blue one. Okay. But when we move from IID to OOD, we can see that the blue curve clearly better than the orange one. That means the second representation is clearly better for the learning of unseen task. Then people may say, okay, how about change the architecture using transformer? Well, here is experiments on what's it? Vision transformer. Well, we have the same result. Blue one is better than the orange. Then people say, how about increase the network size? Use self-supervised learning. Well, this theory model is trained on 1 billion images with 10 billion dense parameters. Well, still the same result. So somehow we get a conclusion for this question. That is, no, we cannot find the risk feature by simply scaling up ERM training. But of course, there are some theory to explain, but I want to use natural language to make it easy to understand. So the reason is that once the optimization process discovered a group of features that are helpful for ID training, there's no motivation to find other features that are not incrementally helpful to training. But even though those features could be substantially helpful to other distribution. Well, because of this confliction between risk feature and optimization, we somehow move from optimization to memory, and we create memory mosaic, which will be introduced later. Here's a brief summary of risk feature. We found the benefit of risk feature is that it can help learning a broader range of unseen tasks. And we also know that we cannot find risk feature by simply scaling up ERM training. Okay, so let's move to the second principle, disentangled representation. We want to reduce the number of examples when we learning a new task. To begin with, I will briefly introduce the benefits of disentanglement, and then I will introduce a pressure to motivate a model to learn disentanglement. And at the end, is an architecture to learn this disentanglement in practice, which is memory mosaic. For the benefits, let's start with a toy example. Say we want to track the position of three moons. There are two astronomers A and B. At every night, astronomer A track the joint position of three moons. And take the note. Night 1, night 2. Okay. He needs to wait until a full period of the combination of three moons to have a good prediction, which is the least common multiple a long time. Okay, instead, astronomer B track each moon separately. So each moon, one node. He only need to wait until the slowest moon. Between the max and the least common multiple, the gap is exponential. So that means disentanglement leads to quick learning. That's the benefits. But this benefit is somehow well known. Then the key question is how can we learn it? What's the pressure that motivates a model to learn disentanglement? There are rich literature in this direction. In the statistical viewpoint, disentanglement is defined on many kinds of independence, but this approach is not reliable, meaning that when we change the distribution, it's not robust. Okay. Then some people, mainly Benju, says we should start from a causal viewpoint. In this direction, disentanglement is defined on active environment, meaning you have different group of environment manually defined, and you change one environment, and you see what's the effect on the other environment. Well, of course, the construction of this active environment is expensive. This causal view cannot be tested without this active experiment. So here we introduce a reliable and cheaper pressure. We call it predictive disentanglement. It is a quick learning pressure to motivate a model to learn disentanglement. We view one nature sequence, for example, one article, one video, as one environment. That means we can create many environments for free. And the training objective minimize the average loss at different sequence lengths. In this figure, we minimize the training loss at x1, x2, x3, and until xd, so the whole sequence. Basically, we want to minimize the area under the curve, okay? And we know that at the tail of the sequence, it's very easy to model to predict because you have enough example. Even using an n-gram, you can have a pretty good performance. Then the training objective instead try to minimize the sequence length to produce a good prediction. This is a quick learning pressure, meaning that the steamroller want to make the head, this part, make it as short as possible, meaning it want the model to have a good prediction with a short sequence. With this quick learning pressure, disentanglement occur when it is more efficient to predict in isolation than together from both architecture and the training data point of view, viewpoint. Then what we need to do for architecture is to encourage this kind of prediction in isolation behavior. To encourage disentanglement, especially predictive disentanglement, we propose this memory mosaic architecture. It's a network of multiple separated associative memory, meaning that it encourages prediction in isolation. And in associative memory, key represent the recent past, value represent a near future. And key value pair, they are treated as a permutation invariant, meaning that there's no position encoding and key is query is key, okay? So let's introduce associative memory. It store key value pair, like the red one, K1 V1, K2 V2, Kn Vn. Then given a key, the blue one, we want to retrieve the corresponding value. This function, this retrieval function is a conditional expectation, right? Then we can estimate this key value distribution by kernel density estimation. For example, Gaussian kernel smoothing. This one, where the beta is some parameter to control the bandwidth of Gaussian kernel smoothing. And once we fix the key vector norm, let's say all the vector norm of key is 1. Let's fix the key vector norm. Then we get this formula close to attention. The only difference is that it only contains key but not query. That means key is query, query is key. It's symmetric. And there is a explicit parameter to control the bandwidth, which is beta. Okay, it's very simple. And how to construct the key and value in this associative memory? So let's say we have a sequence of input x1, x2, x3, x4 until xt. We construct a kt based on the past, meaning kt is a function of xt, xt minus 1, xt minus 2, and so on. And we construct the vt as a near future. So here we say vt is a function of xt plus 1, xt minus 1, and so on. So by this way, we collect a bunch of key value pair of the past. Then given a new key, we can retrieve from the associative memory. This in the simple case, we just say kt is a function, is a linear transformation of xt. Vt is a linear transformation of xt plus 1. Well, of course, there are some expressive cases where kt is a leaky average, is a summary of the past. Vt is a summary of a near future. But we can just focus on the simple case to have an idea about how it works. Then, having this associative memory architecture, I want to evaluate the prediction in isolation bias in memory mosaic. So I do some experiments on the tracking 3 moon problem. On the left, it's one big associative memory. On the right, is many small associative memory, but with the same number of parameters. Well, each green vertical is the period of each moon. We have 3 moon. The red one is the least common multiple of 3 moon. Well, we can see that with one big associative memory, it needs to wait until the full period to have a good prediction. But when we have multiple small associative memory, the prediction loss decrease after each period. And already have a good prediction after the slowest moon. Well, we get what we want. The multiple smaller associative memory make the prediction easier. Let's move to some real world task. And on the left is GPT-2 small transformer architecture with precision encoding, attention, and feed-forward neural network. On the right is a comparison of, it's an architecture of memory mosaic. The CMEM is an associative memory close to attention formula, but with key equal to query, and the norm of key and the norm of key is fixed. And the PMEM is persistent memory. It also contains key value pair, but they are updated by gradient and fixed after training. So it's close to feed-forward neural network. What's the performance? So for the in-distribution performance, we choose transformer as the baseline because it performs well on longest task. We train on 3 to 4 years old tiny story. It's quite simple. We can see with different depths, memory mosaic and the transformer performs closely on this IID performance because we focus on open world and out of distribution performance. So for the out of distribution performance, again, we train memory mosaic and the transformer on 3 to 4 years old tiny story. Then we inference on another data set, which called simple Wikipedia. It's harder for 3 to 4 years old children. Similar to the three-moon problem, memory mosaic is faster and better in adjusting Wikipedia. You can see the red one. So the x-axis is the token position. The y-axis is cross entropy loss on Wikipedia. First, vote model doesn't work very well, but we can see the trend. It's the red one goes the cross entropy is lower and decrease faster. Okay. So we somehow get the feeling about mosaic. It can, for in-distribution performance, it's quite close to transformer. For out-of-distribution performance, it's adjust new environment quickly and better. Well, there are some other example in the paper, in the mosaic paper, but I want to skip it and move to the next principle. So here is a summary of disentangled representation. The benefit of disentanglement is that it can reduce the need of example on new task. And the pressure, the predictive disentanglement pressure is a cheap and a reliable pressure to motivate a model to learn disentanglement. And the memory mosaic is an architecture to learn disentanglement in practice. Okay, inference time learning. So having this rich feature and disentangled representation, we want to reduce the relying of prior knowledge from human designer. So here, inference time learning leverages a memory-based method at inference time to achieve this this goal. So first, the first question is that why we study inference time learning. And the second question is how to build a model to perform inference time learning. And at the end, I will discuss the gap between training on everything approach and the inference time learning approach. What's the performance gap? What's the training data gap? So why study inference time learning? Here is the case. Imagine that we already have a pre-trained feature. It's a rich and disentangled feature. How to learn new task with few example. Oh, we can use transfer learning. We can use fine-tuning. We can use linear probing. So what we need to do is we do some data pre-processing, like BCA or data cleaning. We need to choose architecture according to the dataset size and the prior knowledge. We can tune hyperparameter. We can do cross-validation. We can check the results, and we can repeat. Wow, it's pretty heavy. And what if I have another new task to learn? Well, the answer is try the above process again. As you can see, this learning process on new task involve a lot of prior knowledge from human designers. For example, the data processing, the choice of architecture, and the tuning of hyperparameters. This is, of course, expensive, but more importantly, it doesn't reveal the intelligence of a machine. It reveals the intelligence of us, of human. So here, the inference time learning aim at reducing this this need of prior knowledge from a human designer. Well, let's compare model-based and the memory-based approach when we want to learn a new task. To learn a new task one after another with less prior knowledge and few examples, a model need to shape the hypothesis space because the example from new environment is limited. We also need to avoid negative interference because we want to learn task one after another. Somehow, negative interference is called catastrophe forgetting. So to shape the hypothesis space, memory-based method need to focus on pre-processing, architecture, learning mechanism. Well, you can check it from the paper called Structured Risk Minimization. It's a lot of different mechanism. For memory-based method, you only need to control one parameter, one smoothing parameter. For example, the bandwidth in kernel smoothing, the k in k nearest neighbors. The second issue, negative interference, model-based method just cannot make it at all, no matter how you engineer it or trick it. For memory-based method, it was initially motivated to solve this negative interference problem. One can check this old paper from 30 years ago. But here is a brief, a small experiment from this old paper. So on the first two column, it compared the local weighted regression, which is a memory-based method, and neural network to predict the torques of two jointed arm dynamic. Well, we can see that both neural network and local weighted regression, they work quite well, right? Then we take the learned model to continue train on 10 attempts to make a particular desired movement. Basically, it's another distribution. Then we take the learned model, go back to the first distribution and evaluate. We can see that after the second training, neural network just doesn't work at all. They fail totally. But the memory-based method, the local weighted average, still works quite well, right? So that's the motivation to tell us to use the memory-based methods in inference time learning. Okay. So now I'm going to introduce how to build such inference time learning machine in practice, named Memory Mosaic V2. Okay. It's under review, but you can check from this archive. But let's directly compare the architecture. So on the left, it's transformer. It's a llama kinds of transformer with attention and feed-forward neural network and the rope position encoding. On the right, it's Memory Mosaic V2. We have three memory. We have long-term memory and short-term memory. They are different in attention mask. Basically, the short-term memory only focus on the nearest history. It's something like a sliding window. Okay, the long-term memory instead skip the near neighbors and focus on the far history. Here is the attention mask. And for the persistent memory, we can implement it as a gradient updatable associative memory. We can implement it as a dense neural network or MOE. It doesn't matter. So that's the whole architecture. We have short-term memory focused on the nearest the neighbors. We have long-term memory focused on far history. And the question is why we have this three memory design. Well, here is an explanation. The goal is to disentangle and distribute different features in different memory according to how environment a feature is. Then we can learn new environment efficiently. For example, currently I'm in page 49, so the short-term memory is page 49. I'm in a presentation, but the persistent memory is people can eat and speak. They will not change, no matter I'm doing presentation or having lunch. But this is a lie. It's not a true reason to have this three memory design. The true reason is experiment driven. So we first try to merge long-term memory and short-term memory into one big memory. And we get the following attention distribution of the last token. So in this figure, we take multiple sequences. We compute the attention score of last token correspond to all previous token. We repeat this process multiple times on different token and average. So here the score is average attention score. It's not for a particular sequence. What we can see is that there are two totally different regime. For the nearest neighbors, there is a peak, right? Meaning that the attention score depends on position. But on the far history, the attention score are quite flat, meaning that the attention score is independent of a position. So that's the motivation to have this explicit design of long-term memory and short-term memory, okay? And compare with memory mosaic, we also make the bandwidth beta to be adaptive. That means as we have more example, increase the sequence length, we make beta bigger, okay? But here, beta equal to beta 1, where n is the token position, and the alpha and beta 0 are learnable parameter. Okay, that means as n increase, beta also increase. We also update the feature extractor, but it's just some minor updates. I want to introduce the evaluation process for this memory mosaic v2. The first dimension is persistent knowledge storing and retrieval. It's just some common benchmark. I want to evaluate whether the model can learn the knowledge from training data. So the benchmark are something like MMLU, Arc Challenge, GSM 8K, something like that. And then I want to evaluate whether the model can store and retrieve new knowledge from a new task, a new data. And here I use some ruler question answering task to evaluate this direction. This direction is a prerequisite of efficient in-context learning because you can imagine for goldfish with only 7 seconds memory. How can it learn a 90 minutes movie? It's hard, right? Then we got the very interesting part, in-context learning. In this evaluation dimension, we want to evaluate the ability to learn a new task, a new distribution. And in this dimension, I use a multi-class classification with either semantic label like dog, cat, elephant, or animals label like a class 1, class 2, class 3. Okay. The second one, the animals label is harder because you cannot use prior knowledge from the training data. The model to compare, we train memory mosaic and transformer with two sizes. The first one is around the llama 1.5B size, and the larger one is around llama 8B size. So for the smaller one, we train both model on 20 billion token. So the last one we train on 1 trillion token. And all model are pre-trained on 4K context length and fine-tuned on 32 context length. We choose transformer as the only baseline because for many benchmark in this evaluation process, other approach like RNN, LSTM, or Mamba, this just doesn't work at all. So the first dimension, persistent knowledge storing and retrieval, we choose 19 common tasks, one by one. We can see that for either small scale or large scale, memory mosaic and transformer perform closely to each other. And there's no difference because they share the same persistent memory architecture, basically a feed-forward neural network with SPELU activation. But here is the interesting part. For many common tasks, the long-term memory in memory mosaic doesn't even fire. That means we can take a memory mosaic V2 after training. We remove the long-term memory after training, and then evaluate the performance directly. We can see that so after removing the long-term memory, the performance doesn't decrease. So the last row is memory mosaic. The middle one is a mosaic with long-term memory removed. Or the performance is the same, meaning that this benchmark, they doesn't use the long-term memory. They just use the information stored in persistent memory and retrieved by short-term memory. Let's move to the second evaluation dimension, the new knowledge storing and retrieval. We use a question answering task from Ruler. Basically, there are multiple Wikipedia articles. They are concatenated, followed by a question corresponding to one random article. We don't know which one. And the prompt is something like this. We have document 1, document 2, document 20, then followed by a question. Okay. Well, what we know is that for this kind of task, many memory compression algorithm, this just doesn't work by construction because they cannot store this 20 article in their fixed size memory. Well, one can argue they increase the size of memory, but I can argue I can increase the number of documents. Similarly, many local window methods like alibi, position encoding, sliding window, they also fail for the same reason. So I only compare with transformer. Here is the result. The first table trained on 4K, no fine-tuning, evaluate directly. We can see transformer first lag behind the memory mosaic by around 4%, 5%. But more importantly, memory mosaic trained on 4K can extrapolate contact length 4 to 8 times without any fine-tuning or model adjustment. Okay, just apply directly. And then here, the second table fine-tune the memory mosaic and transformer on 32K context length. Well, here what we can see is that the mosaic outperforms transformer by more than 10%. That's a lot. Here, also more than 10%, meaning that mosaic can effectively store and retrieve new knowledge. And here, the last, the third evaluation dimension is in context learning. We use a multi-class classification with either semantic or anonymous label. Here is one example of input, something like my bank transfer is still not showing up in my account. Then there's some target label, either semantic with some semantic meaning or anonymous. Okay, and we take different example, concatenate them together to perform some kind of few shot learning. And here is the result. So 3 tasks. The first column is banking instance. The input X is some bank domain customer service query, and Y is some category of the query. There are in total 77 query, meaning 77 class. And in the middle is some relation classification. The input X is the sentence extracted from newspaper or web text. Y indicates the relationship between 2 objects in the sentence. And the last column is some emotion classification from Reddit comments. While X-axis is the number of shots, meaning that each shot, for example, in the banking task, contains 77 examples of different categories. It's just the same as the few shot learning setup. Well, and the first figure shows the performance with semantic label. The second figure shows the animals label. Well, what we can see is that as we increase the number of shots, memory mosaic perform better, right? But somehow the red curve transformer cannot benefit from more examples. It decreases as we have more number of shots. And second observation is that there is a gap between blue and red, right? Mosaic outperform transformer by, well, more than 10. One may say, how about increase the size, network size? Because here is a transformer small, around llama 1.5B, trained on 200 billion token. Maybe it's small. So here it's around llama 8B size, trained on 1 trillion token. Same comparison. Well, we got some same conclusion. The gap is still more than 10. And again, the blue curve benefits from more examples, but the red curve cannot. Okay, now we move to the last step. I want to compare the gap between training on everything and inference time learning, meaning that to train a huge foundation model, one can either brutally invest more money, buy new GPU, annotate more data, and simply reuse the old recipe, to say the old architecture training process. Alternatively, one can try a smart technique. What's the difference between those two? So here I want to answer a simple question. How much additional data does transformer recipe need to match the performance of memory mosaic? Because we know that when they train on the same amount of data, there is a gap, the big gap. So to answer this question, I train mosaic large on 1 trillion token and train transformer large on 200 billion, 1 trillion, and 8 trillion token. And I evaluate them on new knowledge storing and retrieval task, on in-context learning task. Okay, so first, new knowledge storing and retrieval. Here is transformer trained on 200 billion, 1 trillion, 8 trillion. What we can see is as we increase the number of training tokens, the performance of transformer increased from 33 to 46. But what we can see is, even though with 8 times more training data, transformers still lag behind memory mosaic by around 6%, from 67 to 53. That means the gap is at least 8 times training data. Well, how about in-context learning? So here we did a similar comparison. Transformer trained on different amount of data and memory mosaic. We can see that for semantic task, which is easier, transformer with 8 times training data, the dot line, start to match the performance of a mosaic. But for animals label, you know, the dot line, 8 times data is still not enough. No way. There's no way to match the performance of mosaic. Now we know the gap. And here is a brief summary. Why we study inference time learning. We want to reduce the relying of prior knowledge from human designers. To perform inference time learning, we create memory mosaic V2. The gap between transformer, the training on everything approach, and the inference time learning, the memory mosaic V2 is at least 8 times training data. And there, of course, there are some other opportunities. For example, one can replace the long-term memory with a hash table or hierarchy memory to cut the inference cost. Well, the whole conclusion of this talk is that AI for the open world shows the intelligence of a machine, not us, not human. To achieve AI for the open world, we need some unique principle and technique. In this talk, I introduce rich feature, disentangled representation, and inference time learning. While this work is still the early research stage of AI for the open world, but it may cost another 5 or 30 years to complete. So there is a huge research space in AI for the open world. So that's it. Thank you for attending. Is there any question?
Yeah, feel free to ask any question or just leave the question in the chat. Okay, it seems that we don't have questions from the audience. Let me ask several questions. So first of all, I think you have 3 important concepts: the rich future, disentangled, and inference time learning. So I'm not sure how the memory mosaic version 2 is correlated with inference time learning. Can you elaborate more on that?
I see. So you want to ask the relationship between memory mosaic and the inference time learning, right?
Yeah, it's not immediately obvious to me.
I see. So maybe we go back to the comparison between memory-based method and model-based method. So in memory mosaic, during the inference, well, the associative memory is a memory-based method. It contains a key value pair, and you retrieve it. You retrieve by kernel density estimation. So it's clearly a memory-based method. And here is the discussion to compare between memory-based method and memory-based method. So basically, in the inference time learning, it want to reduce the relying of prior knowledge from human designers. And to do that, memory-based methods is quite suitable because it can avoid negative interference. It's easy to shaping the hypothesis space. That means to achieve inference time learning, we somehow need memory-based method. But we know that memory-based method is hard to solve the curse of dimensionality because when the dimension is large, when you compute either for example, many distance, Euclidean distance, or cosine distance, you have to solve the curse of dimensionality. That's why this memory-based method was introduced 30 years ago, but people rarely use it recently. But now we got some opportunity by having this entangled representation, by having rich feature prepared to learn a new task. We somehow reduce the curse of dimensionality. We reduce the difficulty so that we can use memory-based method. And well, I agree that memory mosaic v2 and memory mosaic architecturally it's quite close to transformer, but it is transparent. That means you can understand the different components and mechanism easily than transformer. For example, there's no position encoding, so that you can view the attention as a key value memory, which is a permutation invariant. And the key is query requires the key, so it's a symmetric kernel, right? Imagine the Gaussian kernel, it's symmetric. So that's the connection between inference time learning and the memory mosaic and transformer. Memory mosaic is close to transformer architecturally, but it's more transparent. Make it possible to connect it to memory-based method and inference time learning.
Okay, thanks you for your explanation. So you think the self-attention mechanism is not a memory-based method, right?
Self-attention, well, it is a mix of memory-based method and something else.
So yeah, so you think like the position encoding and the separation between the query and the key make the self-attention mechanism a mixed mechanism as opposed to a pure memory-based method, right?
Sure.
I see. So I was also wondering, what's the correlation between this sort of like inference time learning and another popular concept called test time training?
Oh, there are many concepts, test time training, or all these new created thing, test time scaling. The difference is the goal is different. Inference time learning try to solve this one. You just want to reduce the prior knowledge from human designer and nothing else. It doesn't matter which kind of architecture you use. So you see, I introduced inference time learning before memory-based method and the model-based method. That means this inference time learning is the goal I want to achieve. I want to reduce the prior knowledge. And memory-based method currently seems to be a suitable approach. But if you have something else, you can also use it. But the test time scaling or test time optimization, it's not clearly target or directly target on reducing the priori knowledge.
Okay, so again, how does this design principle of inference time learning help you design like the memory mosaic version 2? So like which module is like leverage this idea of inference time learning?
Okay, so maybe
Yeah.
this page is still helpful. So the goal is to reduce the prior knowledge from human designer. So we want to make the hyperparameter tuning, but not explicit. For example, the beta, make it easier so that it do not depend on human. Okay.
Okay,
So
so you think like the three-layer level of memories help the model to learn this process, so to achieve this inference time learning, right?
yes, because see, we have this three memory. Let's focus on short-term and long-term memory because the persistent memory is not far away from a feed-forward neural network or MOE. It doesn't matter. Let's focus on short-term and long-term. And here is the attention distribution for this very far long history. It's independent of precision, and only for the nearest, for the close neighbors, it starts to depend on precision. So from the associative memory point of view, I want different key value pair to be permutation invariant, right? To apply kernel density estimation. So that's the motivation to cut the how to say the sequence into a flat area that is independent of partition, so that I can apply a memory-based method without worry about partition or some other. And with a tail, we can because it depends on position. I can either use Mamba, sliding window, recurrent neural network, doesn't matter.
Okay,
So
so
only you have the idea to make associative memory that is permutation invariant, you can have this split, because that's the motivation.
okay, so you want the model to be commutation invariant about
Yes.
this key value memory.
Yeah,
I don't
yeah.
think this principle is like is against the previous principle of designing those position encoding mechanisms, because for position encoding they want the model to be not permutation invariant, so the model is sensitive to the order of the sequence. So do you think like these two concepts are contradictory, or?
I see. People ask this question a lot. So let's go back to the block. So in associative memory, I want key value pair to be permutation invariant. But as you said, the position information is important. It's useful. I agree. So here you see key is a function of recent history. It already summarizes some kinds of position information. It's a function phi. So I encode the position information here such that in the associative memory, it's a permutation invariant.
Okay, so you are saying that the stored keys and the values already encode the position encoding.
Yeah.
Yeah,
the
but
key, yes.
yeah, but for self-attention mechanism, they also already have the key cache and the value cache out there after applying the rotary embedding. So in this sense, like the rope mechanism is also permutation invariant.
It's not cache. So okay, maybe go back to how to compute key and value. So in normal transformer, key is computed as a linear transform of xt. kt is a linear transform of xt. vt is a linear transform of again xt, right? So let's look at this formula. So currently now in Mosaic, kt is not a linear transformation of xt. It's a leaky average. It's some kinds of weighted average of the past. So each key is a leaky average of the past.
Yeah, so here you have yeah, so here is like you have a very simple linear recurrence to compute this key vector.
Yes. So that key contains the position information.
Why do you use this kind of leaky representation for key, but only use this very convolution for value representation? What is the philosophy behind this design choice?
Yes, good question. So for key, again, this leaky average is the simplest recurrent architecture, right? You can use many other, like with gate, with Mamba kinds of average. That's all good. I just use the most simple case. And based on same principle for value, you know, this convolutional is simpler than leaky average. The convolutional only consider two, leaky average can consider a lot. I want to make it as simple as possible. So when consider two token is enough, I don't consider others. So that's the reason.
Okay.
I try to either consider, for example, for the V, consider the whole history or only consider two. I find consider two is good enough, so consider two.
Okay, so let me rephrase so you can check if I understand it correctly. Okay. So for key, you want the key to encode the positional information, so you use a very simple linear recurrence to do so. This key key vector representation recurrence could be replaced by arbitrary linear RN or nonlinear RN, but you choose the most simplest one. For value, since you want to let each position's value to encode some future information, and you choose several, you blend over several choices and find, okay, this short convolution is good enough to get the
Yes.
performance. Yeah.
Yes, you're right.
Okay. I was also wondering, so what is the correlation between the representation, this angle, and
Yes.
why do you want the VT bar to have the information of the t the value representation and position t plus one? So I can
I see.
understand that this is like very useful for induction head to do induction head within a single layer. But I think there are some previous work using short convolution over both the key and the value vector. So there is a work by Bytran AI. It's called KV shifting. So they apply short convolution over keys and values. It's still causal short convolution. So there is low leakage of the future information. Um, and in their model, they also show that for a single layer, it is sufficient to solve the induction head task. So I was wondering, like, okay, so if this design of a VT update to be conditioned on the Lex positions token could be simplified to like just use a short convolution over the position at t and t minus one.
You mean VT instead of being a function of t plus one and t, it could be a function of t and t minus one.
Yeah. This is what Bytran did. They have a paper called key value shifting, and they show that
Well,
this design can solve induction
it's
head.
based on different kinds of shifting, but the idea is to use the past to predict the future. That's the way you can implement induction height with only one layer. Or you can encode, well, for example, I can imagine a approach. You can encode Vt as a function of V of xt minus one and xt. Then you encode Kt as a function of xt minus one. So no matter how you shift, the key idea is to use the past to predict the future. That's the key to achieve induction head within one layer.
Yeah.
But if you do not use this kind of explicit prediction from past to future, transformer rely on position encoding and asymmetric key query and key to implement the induction head with at least two layers.
Yeah.
There's a work called the birth of transformer.
Yeah, this is very classical results. Yeah, but yeah, like I said, like you can also do convolution in the reverse direction for value, to also to solve the induction head.
It's a modest. It's close because if I encode VT as xt and xt minus one, I need to encode kt as xt minus one. So I still need a shift. So
Yeah,
it's the same.
I agree. This token shifting is very important to do this induction head task or incontinence learning task. Yeah, like recently we have a paper Andrew has a paper called Physics for Language Large Language Model section 4.1, and he had a corner layer, and he showed this short convolution is very useful to do induction head in a single layer.
I see. Yeah.
Yeah. Yeah, so I'm very curious, like whether this direction is important, like whether VT to encode the information for VT plus 1, or in the reverse direction, VT encoded the information from VT minus 1. Do you think they will like eventually perform similarly, or do you think like VT encodes VT plus 1 will be fundamentally more superior?
No, I don't think so. I have one page. So here, okay. So, what in this memory mosaic, VT is a function of t plus 1, and kt is a function of xt. Okay. During the computation of softmax attention, see, we compute until t minus 1. That means in attention mask, we ignore the main diagonal because we don't want leakage, right? Because if we, at time t, if we contain VT, we already contain the information of the future, right? So it's a leakage.
Yeah,
So I mean,
I understand this choice is to avoid like a leakage of the future token. Yeah, after some thoughts, I think like these two design is kind of similar, right? Because here
yeah, they are similar.
Yeah, you
They're
might
similar. It just depends on how you shift. You say when you shift to right, you ignore some main diagonal. When you shift to left, you solve some other problem. It's more or less the same.
Yeah,
the idea.
Yeah, I believe they can achieve similar effect. They are like basically equivalent to each other.
I think the only difference is that whether the current KV pair can be used in this round or it can only be used in the next round. I just think this is maybe the main difference. But I think it's just maybe the current KV, so I think it's similar.
I don't know I don't know the detail of that one, but the key idea is just that after shifting, you create some mechanism to avoid leakage, and it doesn't matter you shift left or right.
Yeah, I think that they just they sum over from from 1 to t, but they just for each k and v they just it's just a linear combination of the current k and v with the past one. So I guess that it's just only just do this shift, incorporate some future information, or do without shift, but incorporate the past information. Yeah. And do you think this is the main reason why the in-context learning performance is much super than the vanilla transformer? Yeah, because that from
Yes.
again V2 that we see that
Well,
yeah.
Just the main reason is the explicit prediction from past to future. That's the one reason. There's another reason is the long-term memory. Well, you can see from this figure, here it's flat, right? And in context learning, it's few shot learning. It should be able to shuffle the order of example without hurting the performance, right? In the classic classification point of view, you are allowed to shuffle the example to have the same prediction performance. That means sorry, what?
No, never mind.
That means a different example, different token position should be treated equally. There shouldn't be any dependence on position. But in transformer, where is it? Maybe this one. Okay. So here it compare the attention distribution of transformer and mosaic. Well, you can see for the transformer, it heavily depends on position, the attention score. That means for some position, it's just always higher than the others. Well, that's not friendly to in-context learning, right? Because it should be permutation environment, different example.
Yeah, I bet this point. Yeah, so I think memory mosaic can kind of solve the problem of like the loss in the middle issue.
Yeah, and I think that the improvement of length extrapolation is also mainly because that you do not use the position embedding. I see. Yeah.
Sure. The
Just
extrapolation
use the gated
comes.
iron kind of position embedding. Yeah, just not the hard one, the explicit position 1, 2, 3. Yeah.
What I can tell you is when I use two separated memory, the length extrapolation getting better. When I merge them into one memory, it's getting worse. But it's still better than transformer, but just decrease the performance.
Yeah, it makes sense.
Yeah, and I have a final question. So previously you show a synthetic task. It's related like 3-moon, right? Can you briefly introduce this task?
Oh, it's toy task. So there it is. So in this task, you have 3-moon with different period, and you want to predict the angle. And to predict this one, we can either have so here it's here. So this network only contain 50 parameters. It's tiny small. It's the total parameter less than 100. Okay, so the task is that you have 3-moon, and there's angle between moon and Earth, and as the moon go, this angle will change. And you have some input, which is the position of each moon. And after learning on a bunch of example, different 3-moon system, the model is tested on another new 3-moon system, maybe from with different period combination. And the goal is to see as providing examples, you can provide 1 period, 2 period, 3 period, and to see how it predicts. So that's the task. The difference is that when you have multiple smaller associated memory, each memory can predict each moon separately. That means after each period, the performance is getting better. Does it answer the question?
Yeah, thank you. Thank you for your explanation. I don't have
maybe not. Do you have other questions?
Yeah, it seems that we don't have further questions.
That's okay.
Yeah, thank you very much for answering so many questions for me.
That's okay.
Okay, thank you again for joining us today. Yeah, very nice presentation, and
Thank you.
yeah.
Yeah, thank you very much today. Yeah, I think many details are very interesting, many design. Yeah.
Yeah, very interesting.
Thank you. Thank you for holding the meeting and the invitation. And happen in the ASAP website to provide a link to the paper, but it's not the correct one. Maybe this one is more represent. But
Okay.
by the way, you just put the one you want. But I mean, this one contain all these different details, scaling up, not scaling up, and rich picture.
Yeah, okay,
But
we'll
you can,
update the link.
Yeah,
and,
we'll update it.
also,
Obviously, we need to
Thank you.
operate memory modules.
yeah, and also could you share us the slides so we can update in the website.
Yeah, I will. Yeah, I see. I will.
Okay.
I will send you the slide. Thank you.
Sorry,
Okay.
could I have one question? It's like in such an
Yeah,
amazing paper.
Yes.
And so basically, does it say that, just, keeping all training examples is the same as having parameters? So it's like a trade-off between compression into parameters, just having examples as they are, right? So you don't need train at all. You just need to have all training examples on hand, right?
Sure. I don't need to train at all. It's as I said, it's a memory-based method. As I have more example, I apply memory-based method like a kernel density estimation. So there's no parameter update. But since I changed the training data, because memory-based method is a lazy algorithm. Actually, the algorithm change as I have more data.
So in practice, how many training examples do you have like in bandit B? Do you need to keep in baby AI, for example, case?
Okay, so here is the case. So for example, in this it's field shot learning setup. And for example, when I have 10 shots of this relationship prediction classification task here, the number of token is around 32K, 32,000. So that means with one shot, it's around 3,000 token for this task.
Okay. So in practice, how do you keep them all? Like, could you keep them in memory, like something like FIS memory?
Oh no, it's not so that much long. It's just a 32K token. I can store them in memory, GPU memory.
Oh, just in GPU. Okay.
Yeah, and when of course it can getting much longer than 32K. So there's some opportunity to implement this long-term memory with hash table so that you can store the token on CPU memory, or you can use some sparse attention mechanism to cut the memory cost and the inference cost. But currently, it's in the GPU memory because it's short enough.
Okay, so where is it going? What do you think about the future? Do you think it's like beyond theoretical value? You think would it be good just to have models like learning with every new examples, just online, completely?
Yes. Well, here is clearly a trend between optimization to memorization, between IID to OOD, and between model-based method to memory-based method. Well, for this inference time learning, the goal is clearly train a model and update model by inference, not by gradient. That means, imagine you want to learn a new task. Say you are a programmer of C++, and now you want to learn Python. They are quite close. We don't need a long time to learn a new programming language. Previously, we need some kinds of fine tuning on new Python textbook. But now with this inference time learning, you got an opportunity to just feed a book to the model. Just read it, and you got the ability on Python language. They change the learning paradigm in the future.
Okay.
That's my estimation. Yes.
How far are we from this future? What do you think?
Well, that's the variance is very large for this estimation. From here, all this 70 page, it cost 5 years, but I don't know how long it will take to finish. Maybe 5 years, maybe 50 years. I don't know. The variance is very large.
Right. So what's currently what is the difficulty? Just why can't we just immediately?
Well, we have a lot of problem in each learning principle. For example, in rich feature, we don't know how. I skipped many pages. We don't know how to make it rich in an elegant way. For inference time learning, we still have some problem to solve. For example, how to support long context. Engineering perspective. Also, how to do cross validation, because in model-based method, we can have a learning signal. We can update parameter according to next token or the target label. But in memory-based method, we don't know how to adjust the bandwidth parameter according to the task. So there are many problems to solve. That's why I cannot estimate the time with a small variance.
But like biological analogy would be just basically we are having like short-term memory, right? Like in context learning, short-term memory, we immediately could put new knowledge to use, right? It's like in context, and like then we kind of during sleep time we kind of
Yeah,
we process
yeah.
it.
Many people and me discussed this sleeping kind of a mechanism. Yes, it's interesting. But we need to implement it. We need to make it in practice. I know this sleeping mechanism is particularly interesting.
Right. So like during sleep we kind of compress memory in
Yes. You're right. Yes.
Okay.
We just don't know how.
Well, I mean, just do what's it, gradient descent, right? And that's how. Like
Maybe.
for now,
Mm-hmm.
is it like
I
one?
mean, yeah. I mean, use memory-based method to learn during the daytime, and during night, use some gradient-based, whatever-based, to compress the learned knowledge into a smaller size, right?
Mm-hmm.
That's your point. Yes, I agree.
Well,
And
thank
thanks
you.
for the suggestion.
It's like my favorite paper for the last, and it was amazingly written, like for the last maybe 5 years. I enjoyed it a lot, including three
Who is
more
the author?
problems.
I see. Thank you.
Okay. Thank you, today.
Thank you.
Yeah. I'll stop recording.